So our goal in this unit is to review and add on to your graphing with transformation. So we're going to use the parent functions that you know from Algebra 2, and then we're going to add on to those. So the first functions we're going to look at this week are going to be the polynomial functions we graphed using those transformations, which are cubic functions and quadratic functions. So the first thing we want to do is we want to remember the parent functions of those. So a quadratic looks like a parabola, and if you remember the set of points for each of these, our parent's the most basic function, and we're basically trying to plug in 0 and the numbers that are easiest for us to deal with around 0 to kind of see what happens with positives, negatives, and zeros. And when you square these values, you get these numbers. So this is something you should have studied in Algebra 2, and you should know those characteristics. So then this is going to give us a graph of what this quadratic looks like. So we have our parabola. And with the parent function, the characteristics, the vertex point right here is 0, 0. It also happens to be the x-intercept and the y-intercept. We're going to go on to figure out how to solve some intercepts in a little bit. You guys should know domain, range, and the table of points. So we just created that table of points. So these are the points we want to really consistently use with our parent function for the quadratic. Our domain is all real numbers because you can plug in anything and square it and still get an answer. Our range here, you can see the lowest point it hits is 0 and the graph happens all above 0. So that's y values greater than or equal to 0, or in the interval notation, that's from 0 to infinity. And 0 has that square bracket because we actually hit 0. Okay. If you remember, we set up the same idea for the cubic function. The difference here is that your parent function is cubing those values. So you're going to get some slightly different numbers, and when you cube a negative value, you actually get a negative result. So that's where we're going to see this curve differ a little bit. Sorry about this. This should be a 2. And so these points, we have 0, 0, 1, 1, 2, 8, negative 1, negative 1, and negative 2, negative 8. So our cubic function doesn't turn all the way around because we can get some negative results. And again, with the parent function, that turning point, or what we would call a point of inflection in this graph, the h and k is 0, 0, and it also happens to be the x-intercept and the y-intercept. The domain is all real numbers because, again, you can cube any number and get any values. And with the cubic, the range is also real numbers because we can get negatives and positives and zeros in every different value. And again, we just created that table of points. And so we really want to connect to this table of points as our kind of starting parent function for those cubic graphs. And now our goal is going to be to graph some functions that put in some of the transformations that you guys are used to. And then one that we're just kind of basically started in our class this week. So we're going to look at first at the quadratics, and this has the characteristics you're used to seeing. And so you see an a value of 2 here, an h value of positive 5. Remember how that works with that x minus h group, and a k value of negative 4. In words, those transformations, and this is something you practiced in Algebra 2, because the a value was 2, let me just double check that that's correct. That is a vertical stretch. The h value was 5. That's going to be a shift right 5. And the k value was negative 4. That's going to be a shift down 4. Now we can literally change everything on the graph, but we explored in Algebra 2 what happens to those points, and we saw that we could also transform them in the table. So you're going to start with that parent function every time. So because this was a quadratic, this is the parent function, and I have to learn this. I have to have it memorized or have the ability to quickly make it. And I want to make a new table of values for my new function that takes into consideration all of the transformations. So what's happening to x? What horizontal changes are there? So the only thing in this list that is a horizontal change is this shift right 5. And when you move right 5 on the graph, what you're doing is you're adding 5 to the x coordinates. For our vertical changes, what happened that's vertical is we have two transformations that are vertical. A vertical stretch is going to take a point. Let's say this point's at 1, 1. And the vertical distance right now would be 1 from the axis. If you're stretching it by 2, you're doubling that distance. That point is going to be stretched further away from the axis. And it's going to take that distance of 1 and literally double it. So the point would now be double the distance from the x-axis. The vertical distance has been doubled. So the way that we do that is we take that y-coordinate and we literally double it, because the y-coordinate is counting how many units we are above or below the x-axis. And then we have a shift down for, if you move points down, you're subtracting from their y-coordinate. So we're going to do that by 4. Now remember, you already did the squaring in the parent function, so we don't need to do that. We need to take each of these x's individually and shift them right 5 by adding 5 to that x coordinate. So -2 plus 5, -1 plus 5, 0 plus 5, 1 plus 5, and 2 plus 5. Now for my y-coordinates, to adjust their vertical distance, I need to take each one of these y-coordinates individually, and I need to double and then subtract 4 from them. So that would be 2 times 4, which is 8 minus 4, 2 times 1, which is 2 minus 4, 0 times 2, which is 0 minus 4, and then just kind of repeating the values that I just did. These are the new points that I should get on my graph. So I'm going to go ahead and plot these. So I should plot the point 3, 4, 4, -2, 5, -4, 6, -2, and 7, 4. And this should give me my parabola. And there are a couple checks you can do on your graph. Notice your h and k were 5, -4, so that's where you expect your vertex to be. And I see my vertex there, so that gives me some confidence in my graph. So my h and k, I see that 5, -4. My domain, again, for all the quadratics, we can plug in anything, is all real numbers, -infinity to infinity. And for my range, I need to look at the new graph. Its lowest point is down here at the vertex, and that's a y value of -4, and the whole graph exists above -4. So my range is y values greater than or equal to -4, or if you like that interval notation, that is a minimum value at -4 up towards infinity. We're going to do the intercepts separately for these to practice our solving skills. So those won't be in this chart, they'll just be right below. Now we're going to focus on a cubic. So the first thing I want you to recognize is this cubic has something new that we've studied through our little investigation, and now we're going to use it, and that's this value of 2 right here. And this works the same for all the functions, just like all the other transformations. And first, we need to separate it so that we write this as that b value can be inside of our cube, but it still has to be separated from our x minus h. So notice there's not parentheses separating that 2 from that x. So you need to rewrite 2 separate from the x, which then makes the 6 become a 3. So this function we are actually going to think of in this format. So it has a negative as an a value, 2 as a b value, and then x plus 3 would be your x minus h quantity. So we're going to think about it like this, okay? So this gives us an a value of -1, a b value of 2, an h value of -3, and a k value of -4. Then I want to remember what each of these do. So I'm going to take those and write out their transformations, and then what does that do to my arithmetic for my points. So my a value of -1, my b value of 2, my k value of -3, excuse me, my h value of -3, and my k value of -4. Okay. So what do these do? So the a value being negative is a reflection, and that's a vertical reflection, or we would say it's a reflection where it flips over the x-axis from above the x-axis to below. That's a vertical change. The b value is 1/2, so this is either a horizontal stretch or a horizontal compression. But remember, in our investigation, we saw that with the b value, it's kind of like the h, it's a little confusing. We actually use the reciprocal to see what change is happening on the graph. So even though the b value is a 2, we're going to be multiplying things not by 2, but instead by 1/2. When you multiply them by 1/2, it makes them smaller, so we would call this a horizontal compression. The h value of -3 is a shift to the left 3, and the k value of -4 is a shift down 4. And now we want to be able to put these things into our table to adjust our parent function points. So first thing, you have to have memorized or have a quick way to make your cubic parent function, which should look like values like these. And then we should understand how each of these transformations affects the arithmetic on these point values to change the distances of the point. So horizontally, my b and my h are what's happening to x. They're the horizontally. I'm compressing, I'm timesing by 1/2, so that x distance is going to get made smaller, times by 1/2. And then I'm going to shift to the left 3, and to move things left on my graph, I subtract from the x coordinate. For my vertical distances, that would refer to my a and my k. I'm causing a vertical reflection, which means if it was a positive y, I want it to turn negative. If it's a negative y, I want it to turn positive. So that negative in front of the y value will change the positivity and negativity. And then to shift down 4, I would be subtracting 4. So now I'm going to go through, and remember, we're going to do that with each of these points. So for -2, 1/2 times -2, and I'll write this out a little bit for those of you that struggle with fractions with this one. We want to think of that -2 as having a 1 over it. And remember, you multiply straight across for fractions. So this would give you -2 over 2. That's just -1. -1 minus 3 is -4. So -2 becomes a -4. So what happens with -1? Again, I'm going to put a 1 underneath that and multiply straight across. So I get -1/2 minus 3. Think about 3 over 1 and make your common denominator. So that's -1/2 minus 6/2 is -7/2. So this is -7 over 2 or -3.5, if that's easier for you to picture it. If I plug in 0, I get -3. Now I'm going to plug in +1. So that's 1/2 times +1 minus 3. So that gives me 1/2 minus 3. And again, I need to make common denominators in order to add the fractions together. So 1/2 minus 6/2 is -5/2. That's -2.5, if you like to think about it that way. And then lastly, when I plug in 2, I get 2 over 2 minus 3. That's 1 minus 3. That's -2. So there are my x values. The fractions make it take a little longer, but the expectation is that you guys can do those arithmetic calculations. Now I'm going to go through and adjust all the vertical distances. So I'm going to take each of these y values and look at their adjustment in this table. So I'm plugging them in here just to adjust them. So the opposite of -8 would be +8. -4 would be 4. The opposite of -1 would be +1, minus 4 would be -3. If I plug in 0, I get -4. If I plug in +1, I get -5, and +8, I get -12. And I'm going to go ahead and I'm going to plot those points. So -4, 4. -3.5, -3. -3, -4, -2.5, -5, and -2, -12, which would be a little bit off my graph there. So I get this really steep reflected cubic function. Okay. Notice that point of inflection, that turning point is right there at our HK value -3, -4, and that's exactly what we would expect. That's why we kind of keep track of it. Our domain, again for cubics, you get all real numbers, and you also get out all real numbers because the curve continues infinitely upwards and downwards. So that's how you're going to graph each function, and you're going to be expected to list these values. The other calculation we're going to ask you to do is to find the x and the y-intercept. So I want to talk first about quadratics. So y-intercepts tend to be a little bit simpler because our equations tend to be written in y equals. And so when you plug 0 in for x to find your y-intercept, you really just have to complete this calculation and follow the order of operations correctly. So we would do what's in the parentheses first. Then our exponents, which is this guy right here that needs to be squared. And then we would multiply before we subtract. So our y-intercept would be the point 0.046, and that should make sense with what we have on our quadratic graph. The x-intercept is a little bit more difficult, and it involves your solving skills, because for x, we plug 0 in for the y position. So notice, solving for x is not already alone. But it is a little convenient that all of our x's are wrapped up inside of this perfect square. So our first goal is going to be to isolate or to get alone this perfect square. So we're going to cancel out the values that surround it. So I'm going to add 4 to both sides. Then I'm going to divide by 2. Because of this coefficient of 2 here. So I have 2 equals x minus 5 squared. Now, to get x out of the squared so I can finish getting it by itself, I'm going to want to square root both sides of the equation, since a square root is the inverse of being squared. So this will give me x minus 5 equals plus or minus rad 2. So big note to yourself here. If you square root both sides of an equation, you need to include the plus or minus. If you don't understand why we do that, it's basically like this. You're using a square root to solve a mystery like this. What squared equals 4? Well, it's not just 2 that if you square it equals 4, it's also -2. So there is when you had something that was squared, you don't know if it was positive or negative to begin with, so you need to include both. Then lastly, to get x alone, we would add 5 to both sides. And so in this case, we have a 5 plus or minus rad 2. We want you to leave it like that. We don't want decimals. These you should be able to write as their exact values. And that means that you leave them in radical form if they can't be simplified to a whole number. So our x-intercept, these are 2 points because of the plus and the minus, is this value comma 0. And you can still check if that makes sense. Rad 2 is like 1 point something. Does it make sense to have 5 plus that 1 point something and 5 minus that 1 point something as your x-intercepts on your graph? All right, we did these two types of functions together because they're really similar. So again, for my y-intercept, I'm going to plug 0 in for x. And again, I just have to follow order of operations. So inside the parentheses, 2 times 0 is 0, plus 6 is 6. 6 cubed is 216. And negative 216 minus 4 is negative 220. So that would be our y-intercept for our cubic function. And if you think that seems really odd, just go back and look at our cubic function. That graph is really steep. It's just going to take so long for it to actually get all the way over to the y-axis. So that makes sense. And then we go through the x-intercept. So again, we plug 0 in for y. And again, this is so similar to the quadratic. It's just that the power is 3. We want to get, since all of our x's are contained inside of this third power, we first want to focus on getting that alone. So I'm going to add 4 to both sides. And then I'm actually going to divide by -1 because we want a positive lead coefficient here. So I'm going to have -4 equals 2x plus 6 cubed. And then to get rid of the cube root, or excuse me, the cube, I do want a cube root just like I wanted to square root. And so that will give me 2x plus 6 on this side. And you guys might be freaking out because there's a negative inside a radical here, but it's a cube root. The cube root of -1 is -1. Okay, we can take cube roots of negatives. So this is negative. I don't know the cube root of 4, so we're going to leave it written as cube root of 4. And now we're going to work on getting x alone. So we're going to subtract 6. So we have 2x equals -6 minus the cube root of 4. And we're going to divide by 2. And so we can leave our answer like this. And we can actually write that as a point. And again, I know that cube root of 4 is a decimal if you approximate it. If you're like, oh, the 2 divides the 6, I want to divide them, you can. But remember that 2 is also the denominator for the 4, so you would still have to write it this way. So that's what you guys want to practice for your quadratic and your cubic, graphing with the transformations, and then also finding the intercepts.